Hey, what's up? Welcome back. Patrick here from All Things Mathematics, and moving on to the next midterm question dealing with matrix algebra. Here we have to solve this system here. X plus y plus z is equal to 1, x plus 2y plus 3z is equal to 4, 4x plus 5y plus 6z is equal to 7. So I'm going to solve this with matrices. Let's practice our matrix algebra a bit. So this line here, I'm going to represent the equal signs. So the first row is all just ones, then this second equation is going to be what? 1, 2, 3, 4, then 4, 5, 6, 7, like that. Okay, and let's go through the algebra and try to get this in row reduce echelon form. So what's nice is we already have a 1 there. And so what I'm going to do is I'm going to turn this 1 to be a 0, and then this 4 here to be a 0. And so what's going to happen, let's actually do it over here. So our new row 2 is going to be our old row 2 minus our 1, right? We can just do 1 minus 1 to make this a 0. And then for our new row 3, it's going to be our old row 3 minus 4 times r1. Right, 4 minus 4 times 1, that would give us a 0 here as well. So what's going to be our new matrix? Well, this first row is going to stay the same, and then we're going to have 0, 1, 2, 3, like that. And then we'll have 4 minus 4 times 1, which would be 0, 5 minus 4 times 1, which is 1, 6 minus 4 times 1, which is 2, and then 7 minus 4 times 1, which would give us 3, like that, right? So that's going to be our new matrix after those two operations. And then if you notice here, basically row 2, row 3, they are the same. So we can subtract them, and we're going to end up getting a row of zeros, right? So there's going to actually be infinite solutions for this system, or we could also say it's going to be consistent and dependent. However, before doing that subtraction, I'm actually going to change this. I'm going to continue the row reduction, just so when we make our final equation, it's going to be a little bit easier. And I'm just saying it's a good opportunity here to turn this 1 into a 0 we could just simply take row 1. So we'll have basically our new row 1 is going to be our old row 1 minus row 2. Okay? And then also at the same time, might as well, I'm going to take row 3. Our new row 3 is going to be our old row 3 minus R2, right? So what's our matrix now going to be? So 1 minus 0, that just stays as 1 as it should. Then we'll have 0, 1 minus 2, negative 1. 1 minus 3, negative 2. Row 2 is staying the same for both of these operations, right, because we're using row 2, and then row 3 minus row 2, we're going to get that row of zeros like that. And so from here, let's set up our new equations. So notice that for x and y, we have these pivots, but notice for z, we do not have a pivot. And so we know that z is going to end up being a free variable. So if we set these up, the first row will have what? X minus z is equal to negative 2. And then we'll have y plus 2z is equal to 3. And then again, this row of zeros, z doesn't have a pivot point, so it's a free variable. So we could let z be any constant. Z could be anything. Let's call it m, like that. Okay, and then this m value here, we could plug it in for the z values in these equations. So we'll have x minus m equals negative 2. So that means x is equal to negative 2 plus m, like that. And then over here, isolating for y, y is 3. If we plug in m for z, so we'll have 2m, bring that over, we'll have minus 2m, like that. And so this is the solutions, basically, right? It's a consistent and dependent solution. There's an infinite amount of points of intersection for this system here. And if you wanted to show it kind of in like coordinate form, we could say, okay, x, y, z What's that going to equal? Well, it's going to equal to negative 2 plus m, 3 minus 2m, and then m, like that, for the z value. Right, so you could pick any, and you could test this too, right? So we could pick any z value, we could pick any m value for the z value. So let's pick, I don't know, let's pick negative 1, okay? So if m is negative 1, then the z is negative 1. What's the y value going to be? 3 minus 2 times negative 1, which would be 5. Then the x value would be negative 2 plus negative 1, which would be negative 3. Then notice that if you plug in negative 3 for x, 5 for y, and then negative 1 for z in all of these equations, they'll all get satisfied. So with this first equation, negative 3 plus 5 minus 1, that would be like negative 4 plus 5, which does indeed equal 1, right? Left side equals right side. Over here, negative 3 plus 2 times 5 plus 3 times negative 1, what's that going to equal? Negative 3 plus 10, 7, minus 3 does indeed give us 4. Plugging in this here, 4 times negative 3 plus 5 times 5 plus 6 times negative 1. What's that going to be? Negative 12 plus 25, which is 13 minus 6, does indeed give us 7. Right? So notice how it works out for this m value of negative 1. You could plug in any real number for m, right? You could plug in 2, 10, 100, negative 1,000, whatever you want. Get the corresponding other x and y values, and you'll notice those equations will always get satisfied, right? As long as this here is holding for whatever m value you choose, right? So that ends up being the consistent and dependent solution for this system of equations. And that's a wrap for the video. Hopefully you enjoyed that. If you want to see more videos like this, please go to my website, allthingsmathematics.com. Over there, all of the videos are organized by chapter, by section. If you feel like you need tutoring at any point, you could also hit me up. My contact details are on the website. Enjoy your day, and I'll see you in the next one. Peace out.